Hello, everybody. Welcome to another episode of The Circuit. I am Ben Beharan.
Hello, world. I am Jay Goldberg, coming to
We
you
would,
from an undisclosed location at a TSA holding cell, effectively.
we think Jay has been obtained by some legal authority, and we're not sure who, based on his background. If you watch this visibly, we would like to welcome Austin Lyons back to the podcast. Austin, how are you?
Cowabunga, I'm good. I'm coming at you. I'm Chip Strat on the interwebs.
That was tremendous. I was going to work that in if somebody didn't at the end. So very good. That was a request from a listener to work in a word. In fact, do this every week because we will be happy to say something random in the middle of a conversation. We'd also like to welcome Paul Karazuba. Did I say that right?
You got it. Thanks for having me.
Yes. Awesome. And Paul, real quick, maybe give a who are you, where you're from, what you do.
Introduce yourself to the people.
Absolutely. My name is Paul Karazuba. I'm the Vice President of Marketing at Expedera. We are an NPU IP startup here in Silicon Valley, and I've spent, it will be 26 years on Saturday in the semiconductor industry, and certainly not that I'm counting the days, but it does certainly make you feel old when you say that.
Tremendous. Okay, so as you might have maybe hinted at, right? What Paul does for a living is relevant to today's podcast, which will show up in your podcast owner as capital NPU exclamation point exclamation point exclamation point exclamation point exclamation point exclamation point. Because the topic of today is NPUs, which if you're new stands for neural processing unit. This is not a newish term, although people are starting to use it more regularly, especially people who did not use it before, which was actually a relevant conversation of a couple years ago. For example, Intel called this their VPU, and many of us were like, stop doing that. Everybody's going to call it an NPU, so you might as well do so. But based on the fact that these things have vector cores in them, Apple almost never referred to it as this until the iPad launch. This was always Apple Neural Engine. And many of us who knew what that was knew it was a neural processing unit, but they didn't want to talk about it. And now out into the world is Qualcomm and Intel and AMD. Everybody's saying we've got NPUs, and it's basically the newest chip on the block, even though it's not the newest. It's the newest because there was a CPU and then there was a GPU and now there's an NPU, which makes it relevant. But that's the topic for today's conversation. So I'm going to lob out to our committee the thesis for why this product exists. We recently at Creative Strategies did a research report on the NPU, and a lot of that work just went in to describe what this is architecturally, the way that it uses a host of cores, everything from vector, matrix, and scalar cores in a symphony of collaboration tied to memory that may or may not be on that block. But the thing that makes the NPU unique, and this is sort of the point that we wanted to make, is that it can process at a much more wattage than the CPU and the GPU core. That doesn't mean that it's always going to be the best place to run an AI workload. Just that if you have something that you want to run, and let's just say that's going to run for 5 hours in the background, right, give or take, the NPU is a great part of that because it can run tops per watt at milliwatts of power. So that's good. So that's the basis. Now, the thesis I want to throw out is the counter argument to what we're saying is, well, just run that on the CPU and just run it on the GPU. But the point that landed with me in this exercise was CPUs and GPUs have other jobs than to run AI and do dense matrix multiplication math, right? So not that they can't do that, but that they might also be playing a game. They may also be visually crunching and encoding video in real time, right? The CPU is running system tasks. It's got a whole slew of things. So do we agree with the thesis that having something that's dedicated to this process so that the other cores can do their jobs do their jobs really well and maybe not be distracted and whatnot, is a sound thesis to approach the role of the NPU. We'll start with Paul, then we'll go to Austin.
So do we agree entirely? While a CPU and GPU, as you have said, are fully capable of running an AI network, there's a difference between can and should. And if you're talking about a battery-powered device, for instance, the difference in battery life can be considerable when you talk about running an AI network in a dedicated purpose-built AI core rather than a more general-purpose CPU or GPU. So yes, absolutely, their NPUs should exist, do exist for a reason, and are more and more becoming a part of chip designs everywhere in every market from what we're seeing.
Yeah, I will keep going with Paul's answer. So if we step back and ask again, like, what is the purpose of an NPU? Why did we ever create one in the first place? Why not just use the CPU or GPU? I think if you look, if you kind of pull back the cover and you look, Ben, you mentioned scalar math, which this is like operating on single data, like 42 plus 2, and vector math, which would be operating on arrays of data or lists of data. And then there's tensor math, so matrix multiplication. That would be a two-dimensional tensor, and then even there's higher dimensions. And with neural networks, the type of math that they do is often vector math and tensor math. Now, you can definitely do these type of operations on a CPU. CPUs can handle vector math. They've got SIMD extensions, but there's limitations, and it's just not as fast as having the native hardware to do it. So sure, you can do it on CPU. It's going to be slower. You can do it on a GPU. GPUs can support vector and matrix operations, but kind of like Ben said, especially on an edge device like a cell phone, the GPUs are being utilized for they're graphics oriented. They're being utilized to drive the display, right? And so if you can instead have an NPU, which would be created, geared for AI compute, lots of parallel computations, tensor and vector, multiply, accumulate units, designed for low latency and low power, then you can both reduce GPU utilization, you can reduce CPU utilization, like you were talking to Ben and Paul. But of course, you can also do it in the most efficient way. You can do it on a GPU. It's going to take extra power. So that's the way I kind of frame it. Is where is the best place to do it? It would be for the circuitry that was designed to do it most efficiently.
And one other thing perhaps to add to that is when we think of networks that are running on devices, regardless of cloud or device or whatever it may be, we tend to think today in terms of maybe, which is funny to say in AI, maybe the more traditional video or audio networks that one might run. If you think of the comparative size of an LLM that you might want to run, and if you're trying to optimize for something like that, where you have 100 times the number of operations that you might have on a traditional network, that level of optimization or efficiency that an NPU is going to give you is going to be dramatic compared to what the same thing would take on a GPU or a CPU. So looking forward, the advantages of an NPU, of having an NPU inside of your SoC, are just going to be more and more with every release of every new network.
I find it kind of humorous that we even have to have this debate, or not debate, we even have to have this conversation to validate an NPU, because like the whole history of semiconductors is just one long succession of multiple chips being merged into one chip, right? Like ALUs, or arithmetic logic units, used to be a discrete chip, 30 years ago, 40 years ago, and now we don't even talk about them, right? But it was a workload, and we needed something to do it, and over time we Moore's lawed it and merged it into CPUs and kind of forgot about it. And I think NPUs fall into that category. It's new functionality. We need something to do it better than the existing solution, so let's just do it. But for some reason, this one is contentious.
Yeah, I want to add on to what Jay's saying. So, I was looking back at the history of domain-specific accelerators, and if you go back to the Intel 8086, it was integer-based math. So if you wanted to do floating point math, You had to do that in software. It was very inefficient. And then the Intel 8087 in like 1980 was a math coprocessor designed for native floating point arithmetic. And so that was like a very early example of a domain specific accelerator, offloading from the CPU, floating point math. And NPUs are sort of like the AI equivalent of that. So this is not new.
Yeah, but at the same time, so where this got a little bit, or I guess where the lack of clarity came from, was it takes up transistor budget, and so everybody was essentially saying like, is that worth it, especially if that block was to get bigger, as you see it get bigger in a couple of different implementations. I would say Qualcomm's, for example, and then you'll see a few other come out at Computex where you're like, wow, that's way bigger. You put way more cores in that than I thought you were going to. But that's where I think it was just misunderstood, right? I think the way that we're digging into it was designed this way is the important role. But just from where I heard people critique this was, even in the early days of some of the big names that we're talking about, were like, I just don't know how much I should give of it if the die, right? I got other things I need to do for core compute performance.
I understand that argument, Ben, and I'll come at this from the business perspective. Yes, silicon real estate is the most expensive real estate in the world. But at the same point, how are you selling how are OEMs selling their products today? They're selling them as AI enabled. They're selling the AI functionality. They're differentiating their products with AI. Chip makers are differentiating their products with AI. So if you look at a value versus cost perspective, I find it hard to justify why you wouldn't want to put an NPU in your system and why you wouldn't want to have a very high capacity NPU in your system to talk about how great your self-driving chip is going to be, or to talk about how great the AI is on your smartphone, or how good your data center is. There's just a million business advantages for doing it, especially when you talk about the cost of silicon. It's not really a debate for most folks.
Right. Yes. Agreed. Okay, so I'd like a little bit more kind of technical, and I say technical loosely, like let's go as deep as we can, but make this digestible, because what I keep hearing, well, let's do two things. I keep hearing TOPS per watt. I don't love TOPS. Nobody loves TOPS. We put in our paper, and I just need to shout this out because I came up with this title. I was very happy, called "Tops of the Morning to You," which is how I described this section. But all to go on to say, like, look, this is why it's being used, but this is not the best metric. So let's start with that.
Yeah.
Let's start with that, and then I want to understand this wattage element of math, of this math.
Sure. So I'll start with this. I am an NPU supplier. I will freely admit that I use TOPS per watt in all of my marketing language that I use. And I will also freely admit, and have done so on my website, that it is a completely ineffective, meaningless measurement of the effectiveness of an NPU. And we all laugh. The problem is it's the most commonly understood. So let me get it. So TOPS is a measure of max times frequency times 2 inside of your device. It has nothing. It's not a real measurement of the actual performance. When you're looking at TOPS per watt, and I published a blog about this, and I'll repost it on our social feed so folks who are hearing this can see it. But when you're really looking at the effectiveness of the system, you need to understand all the underlying test conditions of where TOPS per watt came from. What process node are you in? What frequency are you in? Are you assuming integer? Are you assuming floating point? What actual network are you running? All of that will highly skew the TOPS per watt argument. I mean, I've seen people who post something wild like 300 TOPS per watt, which is absolutely unachievable in 99 and 5/9% of the case, except for the one little corner case where I have something that is so optimized for this particular workload that it works really, really well. So yes, TOPS per watt is a meaningless number, but the problem is the number that most people understand, or at least can somewhat relate to. So that's why it's used.
Yep. Let me take it a level deeper. Paul did a good job and I'll explain really quick for maybe people who don't know, TOPS is trillion operations per second. And when he says max, that's multiply accumulate operations. So kind of at the core of this neural network math, this matrix math, it tends to be multiply and accumulate. And so the two comes from, sometimes these are, these are two operations, you multiply and you accumulate. So that's two. And then, so why people, let's just say it this way, why people can massage it, or how people can massage it, is if it's MAC operations times frequency. The question is, what frequency? Is it a peak frequency? Okay, so that's your theoretical max tops. But what is the actual frequency when you're running a particular workload? And then even then, that also assumes that all of your compute units, all of your Macs are fully utilized. So you might ask, well, what about batch size? If I'm running inference with batch size 1, I'm probably not going to actually exercise every Mac. So you could say, well, what's the achievable tops at this particular frequency at a particular batch size? And then of course, precision, if it's int 8 versus int 4, maybe your multiply add units in 8, let's just say it takes up 8 bits width. And so if you have int 4, that you could do 2 int 4 operations, side by side in that particular unit. So you could basically double that number. And so I think that's why people just say it's a very massageable number, because there's all these things you can do. And even if you go further with tops per watt, the question is, okay, first of all, how'd you get that tops? And then secondly, where'd your watt come from? Is that your minimum power, or is that the actual power that you measured the tops at? So,
and throw on top of that sparsity, compression, and pruning.
Totally.
If you're doing 30% sparsity, you're going to get a 30% improvement artificially, perhaps, in your tops per watt number. So anyone who is looking to evaluate the effectiveness of any NPU needs to look under the hood of where all of the assumptions of tops per watt came from, and for everything that Austin has mentioned and for all the reasons that Ben has said.
So should we stop using it as a metric? And if so, what should we use instead?
Austin, I'll let you answer that one first. I have my own answer, but I don't want to monopolize the conversation.
As a product person, the question is what matters for the end consumer, and tops maybe indirectly matters. But at the end of the day, if they're trying to run like a small LLM, and it's probably something, and let's just say, think, Chat GPT locally or something. It's probably time to first token latency and tokens per second throughput. Now it gets hard to compare, but at the end of the day, like if you gave me like a AI PC, I'd want to fire up and just start asking questions and see how quickly it responds. You could call this almost like a vibes check. And I know that that's not quantifiable, but I just want to see, like, does it feel snappy enough?
Agreed. From an LLM perspective, time to first token is time to first token as well as tokens per second are going to be the key performance metrics. For more traditional networks, I encourage the folks that we work with not to rely on a single number, but to instead, ask suppliers like myself to produce performance estimates in all of the different networks they want to run, and don't rely on a single monolithic tops per watt number, but tell me the 10 networks you want to run, tell me the conditions you're going to run them in, and then have me and my competitors and whomever it may be give you those performance numbers so you see what the real world is actually going to look like, and you're not basing it on some artificial number that, for points made here, probably is not at all accurate for what you're actually going to use.
Yeah. I mean, I think there's 2 points to this. There's the no consumer is going to go run out and buy, hey, I got a computer and it runs at, X number of tops per watt, right? Yeah. What matters is what we're getting in the weeds of is really just that, like, it's going to help your battery life, like a more efficient process, something, right? This is where you're going to get another couple hours out of your battery life if you're going to run really dense applications at the edge.
We all remember when computers were sold on 386, 46 Pentium, and then the frequency, and then it was the amount of RAM. Very few people buy computers for that anymore, if you can even find it. We're looking at how long the battery is going to last.
Yeah.
We're looking at how many, in AI, it's, how fast can I run stable diffusion? How quickly am I going to get, how quickly
Yep.
is my local LLM going to respond to my inquiries? That's what's important to the consumer, not
Yeah.
tops per watt. It doesn't even
Exactly.
need to be defined. Yeah.
Yeah, I totally agree. I think like I said, it's useful for us to just say we've proved efficiency with a metric, and great. But yeah, nobody cares at the end of the day. I want to go back to something that you guys have talked on around the 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 max or theoretical wattage of NPUs, because this was actually interesting to me, because we've been benchmarking a bunch of these Apple's M series, Qualcomm's, etc., Intel's, and you see a range of frequencies. Right, one might be a 10-watt max, one might be an 8-watt max, and so I'm kind of curious how that works. So one, maybe at a technical level, either Austin or Paul or both of you are saying, how much wattage can I peak this at? Like, is that a set number, or could I be like, you know what, I want a 30-watt max NPU, or is it not designed to handle? So I'm just curious, like, how variable is that number? Who sets that number, and are there theoretical limits where you're like, okay, don't do that, then just run it on the CPU, for example?
So I would say that there's no real, well, it depends on what the application for your device is. If you are building something for a non-data center device, you do not want to do any sort of liquid cooling, which is going to put
Mm,
your max power consumption of your chip, let's say 65 or 70 watts, before you're going to need to do some sort of active cooling. Um, but as far as the watt consumption of the AI portion, it really just comes down to the chip maker and what they might be wanting to handle, or what their power budget might be in their system, based on what their customers expect or what their
mm,
users expect.
okay, so it can go
Yeah, I
higher,
would.
basically.
It can. I mean, the silicon can handle it. It's how are you going to package it? Where are you going to put it in the system? And how is it going to be run? That's really the question of how hot it could really get.
Gotcha.
I mean, there are, the H100, which, the darling of the training industry for obvious and justified reasons. That's a 70 to 100 watt at least chip. Granted, it's in a data center, so they have the ability to cool it, but that's not stopping that from being super successful. That same chip stuck in a mobile phone, it's probably not going to be particularly successful.
Yeah. Okay.
Yep, totally. I was just going to add, I would assume that the power is a design constraint that they're designing around. So, they're kind of choosing frequency and power for a given thermal characteristic that they care about.
Gotcha. Okay. Well, I wanted to use that as a segue into because Paul mentioned data center, so I want to get there. But before I get there, let's perhaps bust open a myth that all of these NPUs are proprietary and homegrown IP, which is kind of what everybody wants you to believe. If you're everybody out there, they won't say like we've built this on a quote unquote microarchitecture that's standard, and so therefore we did all of this, like we invented our NPU. Now, when you start looking at that, you're like, okay, well, where'd you get your tensor cores from? Where'd you get your matrix? Where'd you get your vector? And so obviously, maybe they acquired somebody back in the day, and has got it. I think in AMD's case, some stuff came with Xilinx, so there's parts of it that's great. But let's just sort of dispel the myth that this is like some brand new evergreen creation of IP. These companies are using IP that was got from somewhere, whether licensed or acquired. Uh, Paul, you started it. Jump to Austin.
So there are so there absolutely are companies that have organically created their own NPU. They are very likely big companies. Designing an NPU is not a trivial task. Designing one that functions well is incredibly difficult. But yes, one of the secrets of the chip world, and an open secret, I should say. It's not everything on chips has been designed in-house by the manufacturer that you see on the outside of that chip. It would not be uncommon for parts or all of NPUs, for instance, to be licensed from external suppliers, wrapped into a larger SoC, and marketed as internally created. NPUs. This is a weird word to use for any semiconductor, but NPUs are sexy. They're interesting. They're considered to be absolutely state of the art. And to say that we didn't design that ourselves, at minimum, creates a little bit of a public relations and what are you doing? And at maximum says, does this chip company really, what exactly do they do? So yes, there are absolutely NPUs that are licensed from other people that are relabeled, and that's fine. That's the way this industry works. And there are stuff that is created organically. I want to be very clear about that too. Not everyone is licensing them from someone else.
Yeah, two examples. When I was kind of researching where do NPUs come from and what is their history, I think two big company examples. It seems that several people started with DSPs, digital signal processors, as an example of a domain-specific accelerator on a chip. So Qualcomm Hexagon, for example, they basically said, hey, this DSP can do vector math, and it has, high sort of parallelism. It was designed for low latency. Let's just add tensor support to it, and now it will be able to run AI workloads. And so it seems that they took that approach, Qualcomm, and Intel took the same approach. They acquired a company, Movidius, and they have this Shave DSP. And so it looks like Intel did the same thing. They took this DSP, added a bunch of just matrix, multiply and accumulate units, and probably massage the memory layout and everything, and they call it an NPU. And so I think these are just two examples of companies who started with something. One, I think Qualcomm says that they created theirs, and then Intel bought theirs, and then they've sort of like morphed it or iterated it into an NPU.
Has Intel said that explicitly? Have they said that our NPU is from NVIDIA, or is that something you?
So, I mean, if you like Chips and Cheese, a really good website. If you look, they've done some work at talking about it. So I can't say off the top of my head if Intel explicitly said that or if it was pieced together.
Well, it's because when they called it a VPU, they were pretty clear that was Movidius IP, and now that's just become an NPU. That's just a renaming of it. So I think without saying it, because again, like the point I'm bringing up is nobody wants to really say where this came from. I would imagine that Apple's was very similar. Their homegrown DSP evolved into bits of this, and now it is, A&E is what it is. There's other people that I want to talk about next where I don't know where they're getting it from, and that's totally fine. We may not, but my point was everybody wants everyone to believe that this is like, yeah, we came up with this thing, The thing I want to say this though, the thing I think is super interesting about this, because Paul, you mentioned it's sexy, and what intrigues me personally about this is everybody's NPU is different. It's like a snowflake, and from a design standpoint, this shows a lot of creativity, but also philosophy for the company, right? Apple's going to approach this because they'll have a philosophy, as does anybody doing these at an independent accelerator that's not on the block, or so they're all going to be different, which makes it interesting to me, because that will be very telling of architectural design decisions that we just don't normally see in a CPU GPU type of a thing, right? You just throw more cores at it, right? Or frequency scale. Great. This is a totally different thing where we actually get to see designers design. And that's what I find interesting to analyze. So that's my plug of why I think it's interesting.
Yeah, I think it is very. It's been really enjoyable for me to watch this because I try to put this diplomatically. Like, I think Qualcomm should get more credit because they took their DSP, and I think they've actually said this publicly. I think there's a blog post about it of how they rethought their DSP for use as an NPU. And like DSPs were once core to Qualcomm. Like that's a big part of building a modem is that DSP. It goes way back deep into Qualcomm's roots. and now they've sort of modernized. And I think that's a really good story to tell. Movidius, I mean, Intel acquired Movidius 2016, and it kind of that's kind of older stuff. And I'm just wondering, like, how many of these companies are just repurposing old stuff, like maybe Movidius is for Intel. How many people are designing it new from, you know, serious upgrades to older things like Qualcomm does? And like, is that the right approach? I mean, do we need to go back to first principles and rethink how we're doing NPU cores? I think that, you know, I don't know. I think that approach needs to be explored. What do you think, Paul?
I have a biased answer because my company went back to day one and rethought what we believe an NPU should look like. There are a lot of other folks in the IP industry who, I say somewhat sarcastically that they just to basically took a warmed over GPU, CPU, or DSP and created an NPU out of it.
Mm-hmm.
If there was one correct approach to doing this, there would be one architecture in the market, and there's not. There's multiple architectures in the market. We're all doing our best to make sure that we handle as many different kinds of networks as we possibly can. I think the answer to your question, though, Jay, is really time will tell. I feel strongly that you need to build your engine to, if you're going to build an NPU, make it as good as possible at processing neural networks, and don't take any of the baggage of perhaps past usages of that core technology that then became an NPU. We built ours from the ground up. We built ours for the sole purpose of processing neural networks. That is what we believe. It's what Expedera believes to be the best approach. I believe we're right. Perhaps we'll be proven wrong, but I believe that that's the right way to do it.
Jay, we needed a bit more of a curmudgeon comment, by the way, though.
Yes, please.
Yeah, I mean, your optimism is it's hurting me now at this point.
I don't like I'm trying, well, I don't want to name names, but like for the last two years, like you and I have been going to all these conferences and we've talked to everybody, and we asked them like, "Oh, you got that fancy looking NPU there? Tell us about the design." And we're always met with this awkward silence. It's just the weirdest.
Blank stares.
I mean, like, I almost wish they didn't know. I'm like, do they not know, or do they not want to tell us?
No, it was like the forbidden question. You're like, oh, shoot.
Well, I mean, let's be fair though. Anyone who's standing in a trade show booth or anyone who's standing in a technical conference has been media trained. They've been trained to not answer questions from folks like you, specifically because for that exact reason. So if you got an answer out of them, I would be quite impressed by your questioning skills.
Yeah, well, but you're right. I mean, these are a lot of these are analyst specific events where you have a whole bunch of very nerdy people asking very technical questions. And so it has been glaring to me that it's not even a question of media training. It's just like silence.
It could be it could be just a lack of knowledge in the subject. And if you don't want a secret to get out, don't let the secret get out. Don't tell anyone.
Yeah, right.
So yeah.
If I'm just going to throw out there that if we go to first principles, in theory, designing it from scratch, you can make the right trade-offs that you need for neural networks. Now, the question is, when these companies took existing, say, DSPs, what design trade-offs were made, and were those a limiting factor for their NPU at all? Or were those decisions okay and didn't prevent the NPU from sort of reaching its full potential? And that's just kind of what we don't know.
Right, but that's a great question. Like, that's a good question, and I'm asking these people because I want to hear their thoughts on this, and I want to hear
sure.
Right? But
I think it goes back to everyone wants everyone to believe this is secret sauce, and a lot of times it is. It is because that is an approach that they're taking that is their unique design. So I get that. I would love. We asked this because I would just love more understanding on what they're doing, and you will see this. So maybe in a few months we should revisit this, because after Computex, a lot of people are going to come out and give, chips and block diagrams of what's doing what. And I think that'll be interesting to talk about who's doing what. But it's starting to come out, at least at the SoC layer. There's another part of this discussion where I don't think anybody's going to tell us that I want to get to. That's at least vaguely interesting. So let's jump there. So I had a recent conversation with.
Because you
Go
said
ahead.
you said it's secret sauce, right? You said you described it as secret sauce. My contention is that it's not secret sauce. It's three raccoons in a trench coat.
There's my comment. There's our curmudgeon comment. Thank you, Jay. I was desperately needing this. 3 raccoons in a trench coat will be our code word when we're sitting in a word and nobody gives us a straight answer. We'll say there's 3 raccoons right there, man. Okay, so I was having a conversation with a hyperscaler who makes a custom ASIC for AI acceleration, and I basically said, "Give me some details," and they said no. So I said, "Okay, if I was to think that this thing had some vector cores and some tensor cores, would I be in the right direction?" And they said yes. So I was like, so theoretically, this big square block that's maybe 2.5 inches by 2.5 inches is a giant discrete NPU. I think that's interesting. I want you guys to sort of lob out if that's kind of the thesis that we would think about, because I'm sort of saying, one, none of them are going to give us, Amazon's not going to tell us what the microarchitecture for Trainium and Inference is going to be. Microsoft's not going to tell us for Maya. Google's been pretty clear it's tensor cores, great, but they're probably not going to go much, much beyond that. So, but is that a good way? Is that even the right way to think about that? That these are giant kind of NPUs, and I asked the wattage question because, again, this is in a data center. Maybe it can scale higher, but they want these to function as that block that's purpose built for AI workloads. So that's essentially the train of logic I got to where I'm at. So I'm throwing out if that's maybe the right way to think about, Maya, Trainium, Inferentia, and Google's TPUs.
Yeah, I mean, my initial reaction is that is a fine way to think about it as a discrete NPU. I mean, people tend to call those AI accelerators when it's in a server, and then they call it an NPU when it's on the edge.
Right.
But
right.
I think, yes, you are totally correct to say it's just compute built with the correct data type, math, vector, matrix, scalar for neural network workloads. So isn't that an NPU? Totally.
Theoretically, yeah. Paul?
Well, can we have this debate real quick,
Jay?
though? Is
Yes.
an NPU a discrete chip, or is it a block in an SoC?
Ooh. See, we would have need to have defined this in our definition part, which we didn't fully define, because in this case, right, we're leaving. But this is this is a great question. It's the first time I think people I have not heard it asked before. So yeah. So but I don't think it's ever been defined such a way that. And anyway, I'll let you guys chime in first.
If I'm going to freestyle the answer to Jay's question, an NPU is a block in an SoC, and an AI accelerator is a dedicated AI processor or coprocessor, dedicated piece of silicon, let's say. But that's just my Funkmaster Flex freestyle.
Yeah, I guess the counter argument might be like, well, is that chip, Maya Inferentia, does it have a CPU on it, like a little ARM CPU? And so if it's got a CPU and a bunch of Macs, is that really different than your edge NPU?
I don't know. I mean, a GPU is a GPU, whether it's discrete or integrated. CPU generally just its own thing anyway, because that's where this whole world started. So I sort of just default to like, you could take it off, you could take it on. I could put a DSP on, I could take a DSP off. I could put memory on, I could put memory off. Like if the function is the same, that's sort of why that. But that's why I 100% don't think anybody in making a custom ASIC is going to call this an NPU. My annoyance was that it was so ambiguous that no one had any idea what it was doing, that I was just like, we at least need to think about this somehow. and this custom built thing, even if it's a coprocessor that just handling AI workloads, makes sense to think philosophically like we think about NPUs. That was the train of logic.
Totally.
Yeah, I mean, my sense is that increasingly NPU is the block inside the SoC.
That's how people refer to it. Agreed.
Yeah,
Agreed.
I think that's where we're landing. But
yeah,
yeah,
only because again, nobody's going to call it that, and unless the wild card to our world is in 2 weeks, Apple goes, we're making hyperscaler chips. And oh, by the way, we've turned A&E into its own engine, and it's an NPU. Like they could screw everybody up, but regardless, that's a different conversation. If and when we learn about Apple's data center efforts. But I would tend to agree, only because nobody's going to call their giant chip. But I did ask the wattage question in an attempt to perhaps make a distinction. If you told me that theoretically you can only throttle these to a certain amount, then I would say, cool, then it probably is always going to be on. But if somebody could make an NPU and it throttles to 150 watts, and that's not theoretically impossible, then it scales. It scales to data center coprocessors.
I have a question for the group. Going back to are everyone's NPUs different or are they similar? Do you think NPUs, let's talk edge or AI PCs, will those be a point of differentiation, like the hardware itself?
Will it be let me make sure I understand your question, Austin.
Yeah. I buy these laptops because they have the A&E and it's or whatever. They have so-and-so's NPU in it. And it's always snappier than, kind of like an Intel versus AMD. Like I'm buying it because of the NPU.
I think consumers, for the most part, are more accustomed to buying what a device is going to do for them rather than a code name of something that's inside of a device. Let's just say whether it's an XYZ processor or whatever it may be. Marketing is skewed toward usages. It's skewed toward how is this device going to make my life better, easier, quicker, faster, whatever the word you want to use is. I'm not sure that I would see there being, from the consumer point of view, people buying because it contains a particular chip, containing a particular function that's different, containing a particular use case that is unique to a specific manufacturer or OEM. Absolutely absolutely could see that as a buying decision. But as far as, just simply containing a chip from someone, I don't know about that.
So if I buy a Copilot Plus PC with the Qualcomm, Snapdragon in it, and it has more interesting or better AI functionality than a different OEM, would that be differentiation then? Even if the consumer doesn't know why?
So I'd say it this way, though. Let's just say hypothetically, vendor B, because I don't want to name anybody, comes out with Copilot Plus PC, and it gets horrible battery life because it just wasn't designed well. Now, the consumer is not going to be like, oh, vendor B is really bad. They're just going to be like, those things don't get 25 hours of battery life. This one does, and that's a pain point to me. They're going to say, okay, I'm going to prefer the one that I'm going to go toward the one that got better battery life, right? But that perception will come out through whatever. But that's, to Paul's point, that's the end result of the implementation that leads to the use case or the value proposition that you care about. So that's what they care about, is the end. The secret sauce in the middle just gets to that. And if a vendor doesn't do a good job of implementing this, then that's definitely going to impact real world performance, which will then skew people toward their buying decisions. That's how I would look at it.
I think it's even worse than that. Consumers will not care about any of these features. It is not differentiated to them because there are no good consumer use cases for AI right now, right? At least none that consumers are aware of, right? Maybe some of these Microsoft features take off. I don't want to knock them, but unless there's some surprise hit there, consumers aren't going to care, so they're not going to care about the AI features in the phone. Conversely, if you're running an AI PC, and to your point, Ben, if it's really bad performance because of the chip maker is not going to get blamed. It's going to be 50-50. It's either going to be the OEM who made the laptop, or it's going to be Microsoft, because consumers know both of those. And so, right, and if consumers find, oh, this was it the recall feature, it's like really, if it's like stutters, people are going to blame Microsoft. If the battery life is terrible, they're going to blame HP or Dell. Right?
Yeah, I would agree with that.
But the flip side of that is, if we can actually get a really good consumer use for AI PCs, and one of the chip vendors has a real advantage there, then that's their opportunity to build the Intel Inside brand, or for Intel to reinforce the Intel Inside brand, right? And I think that's Qualcomm's big opportunity here. Is if somewhere down the road some great feature shows up and they have a big advantage, then they go spend $1 billion on a consumer marketing campaign. It'd be huge for them,
right?
But but the problem is, by the time we get that feature, there's a decent chance Intel and AMD will catch up, and so.
Right. With the exception that, and I would agree that there will be more parity than not. However, this one block is probably the one that for at least the next couple years we'll see the greatest year-over-year performance on, as they throw more transistor to it, as they throw more matrix or tensor cores at it. And I don't know what that's going to yield yet, to be honest with you. Like, we could be building something that no one gets used and transistors are left on the table. Maybe. I don't know. I'm just saying, like, that's the one, like, we always scrutinize. I want to see IPC gains gen on gen. Like, it's just really hard. However, AI compute gains, we're going to see that at the edge. And now it's just, like, to the whole conversation, developers need to absorb that software, right? In the same way that throw more GPU compute in the cloud and all of a sudden the model gets bigger and they chew up every single one of those tops and flops. We need the same thing at the client edge, that give them more compute, in this case, NPU compute, let developers go wild. Let's see what happens. We don't know. But that one block is going to see drastic performance year over year because everybody's investing in it. And it is the one thing you can get a whole lot more compute at the edge. So we'll see where that goes. But yes, we are still all fishing for these wonderful use cases that really most normal consumers don't even care about at the moment. So anyway, but that's the nitty gritty of of that bit. Okay, let's just throw some parting thoughts out to the subject, since we're almost at our longest podcast ever, but this was a rich discussion, so I'm sure everybody will enjoy it. Last sort of thoughts, if you will, on the NPU as a whole, and let's just say specifically, can we make any kind of prediction at this point about where this goes, other than what I just said, which is it's going to get more compute? Is there anything else we can say, like, watch for this as SoC vendors evolve this strategy?
I'm going to make my prediction that you are going to see NPUs on 90+% of chips, other than really small discrete chips, within the next 3 to 4 years. You're going to see them absolutely everywhere, of varying sizes, of varying capabilities, in almost every market. You're going to see them in refrigerators. You've seen them in smartphones. You're going to see them in cars. They're going to be absolutely everywhere.
Great prediction. All right.
I'll go a step further on that. I think you're even going to start seeing them in some pretty small chips too. Maybe not full blown crazy ones, but like decent sized ones in microcontrollers. I think that's coming sooner rather than later.
My prediction, and for the record, if I'm wrong, this is Austin from Chipstrap, is we can check on this in a year. I think multimodal LLMs plus NPUs will create a very interesting proliferation of awesome use cases for hands-free edge devices. So think, like smart glasses, like what we hoped Google Glasses
Sure.
would be.
Right.
Because now it can understand visual input. It can understand your natural language way better than Siri ever could. And therefore, I think, and by the way, NPUs bring the cost to a developer of inference down maybe to zero. They don't have to rent or buy NVIDIA GPUs. They've just got it right there. And so maybe we'll see tons of little tiny consumer edge apps being built over the next couple of years. And maybe a year from now, I'll be wearing a pair of those for our follow.
I hope so too, dude. I like want my Meta glasses to do all that stuff already, and I'm annoyed they don't, because theoretically it should. Maybe just not on device, but to the cloud, like do these things. So yeah. All right. So my wild one will be, and this might ruffle feathers of some people who I know are listening to this. NVIDIA will make an NPU and either put it on board and or integrate that onto perhaps a client SoC, but a company that has no NPU at the moment and is the AI king will make one in the not too distant future. So there we go. Well, gents, Austin, Paul, thanks for joining. Austin, everyone can find you at Chipstrat Substack.
Yep.
And again, I said this before, the best Twitter handle, the Austin Lyons, Lyons. And Paul, maybe quickly, we mentioned your company. Just give it, where can people find you, read your stuff, your company, etc.
Sure. You can find my company at expedera.com, expedera.com. You can find me on LinkedIn. And that's the best way to get in touch with us or see what we got going on.
Awesome. Thanks for listening, everybody. Appreciate your comments. And until next time, cowabunga. I got it in twice.
Thanks, everybody. Tell your friends.
Thank you.
Bye.